The first optimization problem that we look at is the question that asks, what is the best way to charge a battery pack? And we can pose this question as a fixed time problem. We could even pose it as a minimum time problem. Here we're looking at a fixed time problem where we say, suppose I know in advance that I have a certain number of seconds or minutes available to me for charging a battery pack from the present state of charge to some desired final state of charge, and I want to in some way optimize the life of the battery pack. Then how am I going to accomplish that? This particular problem is one that lends itself well to a methodology that's called nonlinear programming. And we are not going to study nonlinear programming in this course, but please remember we have ECE5720, which is a course that deals with engineering methods of optimization, and it does talk about nonlinear programming and how to do it yourself and so forth. Optimization is a really big deal in engineering and in the future of battery management, as the way I see it anyway. The nonlinear programming has different methods. One method is sequential quadratic programming, SQP, sometimes you see in the literature. And MATLAB in the optimization toolbox has the function fmincon to minimize some objective or cost function with constraints. That's what the con is for. And we'll see how we can map our fast charge problem into the framework required by fmincon. So nonlinear programming in general, it's a very generic idea that has just many applications in engineering and in math and in science, I suppose. We try to find solutions to problems that can be written in this framework here, and the framework might seem limiting at first, but with a little bit of experience, it's actually possible to write many things this way. We want to first we define a cost function f of x, and x are the variables that I can change. In our case, x is a vector of current versus time for charging the battery pack, and f of x is some accumulated degradation, and I want to find the vector x of current versus time that is going to minimize the degradation that occurs. So that's why this is a cost function. A big value of f means that there was a high cost involved with the proposed solution, with the proposed x. A low value of f says it was a lower cost or a better solution. And fmincon, or nonlinear programming in general, is trying to minimize this cost function f by choosing a vector x to do so. And so this is saying I return the argument to f of x that minimizes f of x. In other words, I return the x vector that minimizes f of x, and we call that x star. X star is the best solution that I found. It might not be the best solution that exists, because there could be many local optima or local minima to that cost function, and we're really guaranteed to find only one of those. Maybe it's not the overall global minima, but we'll find at least a decent solution, although maybe not the best solution. So there's quite a bit of art involved also, not just science, but art to learning how to use these optimization routines. If that's all there was, this would be an unconstrained optimization problem. And in MATLAB, I could use fminsearch.m or fminunconstrained.m. Both of those use slightly different methods, but try to accomplish the same objective, which is to find that minimizing x. However, for us, there are constraints on the problem that we need to satisfy also. So remember, x for us is going to be a vector of cell current versus time going into the future. And we want to satisfy, possibly, some nonlinear function c of x be less than or equal to 0. C is a nonlinear function that we supply, so there may be a nonlinear inequality constraint that is imposed on those variables for whatever reason. And that function has to be written in such a way that I can always write it as the constraint is less than or equal to 0. So if I have some function 1 of x is less than or equal to some function 2 of x, I have to rearrange it to be function 1 of x minus function 2 of x is less than or equal to 0. We often have to do some minor manipulations like that, and then everything on the left side here, we call that c of x. It's possible that we also have some equality nonlinear constraints, so we say that the solution has to satisfy some nonlinear function of x exactly. So we give f min con the c function, and we give it the c equality function also, both of those being nonlinear. In some cases, it could be that we have linear constraints. So if I have a linear inequality constraint, I can write that as ax less than or equal to b, or ax minus b less than or equal to 0. That would be another way of thinking about it. And I can then supply the A matrix and the B matrix to f min con so that it can accomplish that constraint. Or maybe I have linear equality constraints, so I have aeq equals times x equals beq. Of course, the linear constraints could be written as a subset of the nonlinear constraints. However, the optimization is more efficient if I can separate out the linear and the nonlinear constraints just based on the methodology that's used. And finally, we have that x must be bigger than some lower bound and less than some upper bound is a different constraint directly on x. And that's it. That is the framework for nonlinear programming that is solved by fmincon.m. So I think we said all this. We said that nonlinear inequality constraint c of x less than or equal to 0 must be satisfied c equality of x equals 0, ax less than or equal to b, a equality x equals b equality, and x between the lower and the upper bounds for all entries in x must be satisfied. And the user specifies what is the cost function f of x, what are these nonlinear constraints, what are the linear constraints, and what are the lower and upper bounds. Those are all passed into the fmincon.m. To make this work with our problem, we have to find a way of representing the fast charge problem so that it looks like this. Fast charge needs to look like that somehow. And if we can make fast charge look like that, we just call fmincon and we get a solution. We are going to choose, as I've mentioned already, x to be a vector of cell current versus time. F of x is some estimate of the cell degradation that is caused by that particular vector of current versus time. And the other functions in matrices are chosen to make the problem work. I'm not going to leave it there. We're actually going to go through all of the details to show how to set up these matrices. So let's see how to do that. This might be a more natural way for us to express the problem we're thinking about. We might say, I want to find the optimum vector of current versus time, I star, which is the thing that minimizes this overall cost which is the sum from k, the time index k equals 0 up to capital K minus 1, of the side reaction. Here I'm thinking J, capital JS, is the total lithium loss during that time interval based on that particular index into the I vector, I sub k, and the state of charge at that time and the temperature at that time, for example. Remembering that lithium loss, the flux was negative, I need to multiply it by -1 to get a positive lithium loss, to get something positive that I want to minimize rather than something negative I want to maximize. So basically just reading this is I want to find the vector of current versus time that minimizes the total lithium lost when I'm charging this cell. We have constraints. We may still have some design limits on state of charge, that the state of charge at every point in time k must be bigger than Zmin and less than Zmax. We could set Zmin to 0 and Zmax to 1 if we want to have basically no limits at all. But here we're thinking about having at least some possible limit on that variable. We also want Z at the final time, capital K, to be Z end. So Z end is our desired fully charged point, whatever that is. Maybe I want to charge up to 90%, then Z end is 0.9. And I also might have some electronics limits on the current that could be applied. So current at every point in time is bigger than negative Imax and is less than positive Imax. Those are some constraints we might want to put on the problem variables. And we also have the constraints of just the plain dynamics of how state of charge works. And state of charge, we know, works like this. So at any point in time, Zk is equal to the initial state of charge minus the sum for J equals 0 up to K minus 1, or Z less than K, of the current at time J times delta T over Q. Here, for simplicity's sake, we are ignoring the Coulombic efficiency, assuming it's close enough to 1 that we don't really worry about it too much in this computation. It actually makes things quite a lot harder if we put Coulombic efficiency in, because it's a nonlinear equation. It depends on whether the I is negative or positive. So again, in words, we're saying we want to minimize capacity loss that would be experienced by a cell if we were to start at the state of charge Z0, which is there in all of the equations, and end at SOC Z end, which is there at all of the equations, over a period of k sampling intervals. And we see k there and k minus 1 there, where current is limited between plus and minus Imax, which is there, and SOC is limited between Zmin and Zmax, which is there, and the standard SOC equation holds, which is this, and we're minimizing capacity loss, total capacity loss, which is that. So all of those pieces are present in this formulation here. But if you compare this to the standard formulation of nonlinear programming on the previous page, you'll notice that they're not the same. There are definite similarities, but they're not the same. And we're going to have to spend a little bit of time changing this definition here, or this set of equations, so that it fits within the framework required by nonlinear programming. It's going to take a few minutes, but it's really not bad at all. Once you see how to do it once, you can probably do it immediately again for a lot of different other problems. So let's look at the state of charge equation. We are going to define a vector here of state of charge at time 1, at time 2, at time 3, all the way up to time capital K, which is the end. And for every one of these, we write out in kind of long form how that state of charge depends on the input current vector x. here. So x is current at time 0, 1, etc., all the way up to time k minus 1. So Z1 is equal to 1 times the initial state of charge minus delta t over q, all multiplied by 1 times I0, and that's it. Z1 equals Z0 minus I0 delta t over q. That's it. Z2 is equal to Z0 minus delta t over q times 1 times I0 plus 1 times I1. If you go back to that summation formula, I'm summing up all of the i's at time less than or equal to the final time here that we're looking at, time 2. And you keep on doing this for all of the states of charge up into and including time k. We get state of charge at time k is 1 times Z0 minus delta t over q times 1 times I0, 1 times I1, 1 times I2, 1 times I3, all the way up to 1 times Ik minus 1. So this is the state of charge equation. This equation right here, converted from a summation formula into a vector matrix equation that's going to be far more useful for the purpose of setting up a nonlinear optimization problem. In this solution, we have all of the currents from time 0 to k minus 1 in vector x, just like we said. That's the profile of current versus time. We have this matrix here, which has a very interesting structure. Notice that in this matrix, all of the entries on the diagonal and below the diagonal are 1, and everything above the diagonal is 0. So this is a lower triangular matrix filled with 1s, and I'm going to call it LT for lower triangular. This here is a vector that's full of 1s, and it's a column vector, so I'm calling it CV for column vector of 1s. And everything else are numbers that are supplied to the problem. Z0 is a known number, and delta t over q is, the sample period is known, the capacity of this cell is known. In particular, so that allows us to write all of the states of charge in one equation, which is quite handy. But in particular, we can look at the constraint here, this equality constraint that says that at the end, we have to achieve a desired final state of charge. So I can pull off the last row of this equation and say that zk equals z0 minus delta t over q times this matrix of 1s times x, and I desire for that to be equal to z end. That is going to be part of my equality constraint. And for me to write that in terms of something required by fmin_con, I rearrange this. So I have, looking at this here, I'm going to have z end minus z0 equals minus delta t over q times all of these 1s times x. I could write it that way. I chose to write it a little differently. I chose to multiply both sides by q over delta t. So I have z0 minus z end over delta t all times q equals all of these 1s times x. And there it is, except this should be z end. So z0 is known, z end is the desired endpoint, that is known, q over delta t is known, so I can compute the B equality. In this case, it's just a scalar. It could be a vector in general, but for our problem, it's a scalar. And AEQ is just a bunch of 1s, a row vector of 1s, so that is also specified. So that is going to be our equality, linear equality constraint for fmincon.m. We go back to the state of charge equation, and we say that the state of charge must always be bigger than Zmin and less than Zmax, and we can use that matrix vector formulation to accomplish that. So we said that this here was equal to Z1, Z2, all the way up to Zk, and that vector of Z had to be bigger than Zmin. Well, in MATLAB, I can't just give it a scalar Zmin that corresponds to a vector of things. I have to give things the same size. So I can say, well, each entry is less than Zmin, or greater than Zmin, rather. So 1 times Zmin, 1 times Zmin, all the way down to 1 times Zmin is less than Z1, Z2, Z3, all the way up to Zk is the proper constraint. And looking at it then from this perspective, we can rearrange this to make an inequality, linear inequality constraint on X. So let's do that. I'll erase some of this noise so we can see how to do that better. I'm going to take this and bring it over to that side of the expression, remembering that this we called CV. So CV times Zmin minus CV times Z0 is less than or equal to minus delta T over Q multiplied by this lower triangular matrix multiplied by X. And I am going to multiply both sides by minus 1. When I do that, remember it changes the inequality. So it's going to make that plus, and it's going to make that minus there when I do that. And then I'm going to multiply both sides by Q over delta T, and I get lower triangular times X, switching sides, is less than or equal to Q over delta T times the CV vector times the constant Z0 minus Zmin. That is one inequality constraint, but I have another one, so I'm not done yet. So let's remember this and also look at satisfying Zk must be less than or equal to Zmax, and go through the same argument in the same steps. And when we do that, we get minus Lt times X is less than or equal to Q over delta T times Cv times Zmax minus Z0. Putting the two constraints that require that the state of charge be bigger than Zmin but less than Zmax together on top of each other, I stack these equations. So I have Ltx less than or equal to Q over delta T times Cv Z0 minus Zmin is one set of equations, and negative Lt times X less than or equal to Q over delta T times Cv times Zmax minus Z0 is the other set of equations. Stacked on top of each other, I get this overall matrix which has ones and zeros and minus ones and zeros in it. Basically is on the left hand side, all multiplied by X, and so forth on the right hand side. This matrix is the A matrix for the inequality, the linear inequality, and the right hand side is the B matrix for the linear inequality. So if we go back to what we've looked at so far in here, this is a mess. We so far have satisfied this constraint, and we have satisfied this constraint, and this constraint is built into both of those, so I don't need to satisfy it directly. I do have one more constraint left, and that's the constraint on current itself. So let's look at that. We have that the lower bound is equal to negative Imax times a column vector of 1s, because I have to specify a lower bound for every value of current. And the upper bound is Imax times a column vector of 1s. So that will allow us to satisfy the constraint on current. And that's all that's left is to give a cost function. In this problem, we don't have any nonlinear constraints. And given what we've seen so far, this cost function might use the instantaneous lithium loss due to SEI growth, or due to overcharge, or the sum of both. Based on future models of degradation, we could make that cost function anything that we wanted that would seem reasonable. So, to recap this section, we've introduced the framework of nonlinear programming. And it's a very rigid framework that you have to specify your problem in a very specific way. Then we looked at the problem that we want to solve, which doesn't automatically satisfy that framework. But we were able to do some manipulations to the equations to come up with these matrices for A equality, B equality, A inequality, B inequality, and the lower bounds and the upper bounds. And we can specify a cost function. So in fact, the fast charge problem can be very readily written in a nonlinear programming framework. And then we just call fmincon.m. And there's probably some ways of making this efficient or inefficient. I'm not going to worry about those too much here. I would like to present some results, though, that are based on the models that we've seen in the last couple of sections, so you can get an idea of what the output of this nonlinear optimization looks like. And that's what we're going to do next.